distributed systems have to deal with a number of rules like Amdahl's law and Gunther's law of universal scalability. But in addition to that, they have to deal with something that we call the CAP theorem as well. Now, the CAP theorem states that a distributed system cannot provide more than two of the following: consistency, availability, and partition tolerance. We'll define partition tolerance in a moment, but first let's talk about the diagram that we see here. We see on this diagram that we have availability, consistency, and partition tolerance on the corners, and then we have the sides labeled as AP, CP, or CA. CP stands for consistency and partition tolerance, AP is availability and partition tolerance, and then CA is consistency and availability. Now, what we see is that if we pick a point anywhere within that triangle, as we move that point towards one of the sides, the CP side, the AP side, or the CA side, we're always moving further away from the opposite corner. So if we want to move towards consistency and partition tolerance, we can only do that by moving away from availability. In other words, in order to achieve partition tolerance and consistency, we have to sacrifice availability. If we want to be available and partition tolerant, then we have to sacrifice consistency. Now, the ideal situation would be, well, what if we could be consistent and available? And the diagram would suggest that maybe we could do that, but the reality is more complex. And in fact, we'll see that consistent and available isn't really one of the choices that we have. So let's define partition tolerance. The system continues to operate despite an arbitrary number of messages being dropped or delayed by the network. So any distributed system is always connected by some kind of network. The nature of that network may vary, but there's always some sort of network connecting these distributed systems. And that network is never going to be safe from partitions. Nobody has built a network yet that is safe from partitions. Those partitions can occur due to a number of different problems. Somebody might cut a network cable. We could have a failure in a router. It could be something like a node in the network going down. So the hardware that hosts that piece of the system could fail. Could be a software failure. It could also be routine maintenance. So we might actually shut down a node in the system in order to upgrade it or perform some sort of maintenance operation. When that happens, when the partition occurs, whatever the nature of that partition, messages can't get across that partition. Those messages are going to have to be either dropped, or you might buffer them somewhere and then deliver them at a later date, so they'll get delayed. But we can't deliver them as long as that network partition occurs. The network partition could be short or it could be long-lived. It might last milliseconds, microseconds, or it might last hours, days, or even forever. We theoretically may never fix the problem, although arguably if we never fix the problem, we've got bigger fish to fry. Now, the CAP theorem is really about what happens when a partition occurs. So when a partition occurs, a distributed system has two options. We can go for availability and partition tolerance, which means that we sacrifice consistency, allowing writes to both sides of the partition. Then when the partition is resolved, you need a way to merge the data in order to restore consistency. So in this case, as long as the partition has occurred, you're going to continue to allow writes on both sides of the partition, but now what happens is the two sides of the partition are diverging. They're no longer in agreement on what happens. In that case, what we will do is when the partition goes away, we need a way to merge that data in order to restore the consistency. We need to decide who's right, basically, or combine the answers in order to determine the right one. So that's the AP situation. The other option is CP. In this case, we are aiming for consistent and partition tolerant, so we sacrifice availability. In this case, we disable or terminate one side of the partition. This means that during the partition, some or all of your system will be unavailable. Anything that is on the side of the partition that can't be reached, that has been disabled or terminated, that portion of the system will be unavailable. So this is a CP system. We maintain consistency in this case, but we lose availability. Now, some systems do try to claim to be CA. They say that we are both consistent and available. The way that they do that is they pretend that they're not dealing with a distributed system. So they basically say, look, we don't have a distributed system. We only have one node. And because we only have one node, we don't have to deal with the CAP theorem. We can be consistent and available. That's not really fair, because if you have only one node, for example, then what happens if that node goes down? Well, if that node goes down, then you become unavailable, in which case you are actually a CP system. Now, then those systems might claim, well, yeah, but we deal with that by having replication. So we have a master-slave setup where the slaves will fall back to the slaves in the event of failure of some kind. But the moment you introduce those slaves, you're back to a distributed system problem. And when you have those slaves are typically updated asynchronously. In other words, they're dealing with stale data. That means when you fall back to a slave, you've sacrificed consistency. Yes, you maintain availability, but you've sacrificed consistency because you potentially have lost information that was on the node that went down. So the idea of a CA system doesn't really exist. You're always choosing to be either available and partition tolerant or consistent and partition tolerant. You only have to make that choice when a partition occurs, but no matter the system, a partition will always occur. So we always have to make that choice at some point. Now, the CAP theorem is a little more complex than we have indicated here. We've given the impression that maybe it's a black or white choice where you pick consistency or availability. It's often more subtle than that. So systems that claim to be CP, they're claiming consistency, often have areas where they're not always consistent. So if you look at distributed databases like CockroachDB, for example, I believe CockroachDB operates in such a mode where they say we are consistent, but if two operations happen within a certain amount of time, something called the clock skew, then we can't necessarily guarantee consistency within that clock skew. So they've sacrificed some consistency in that case. Systems that claim to be AP often have areas where they're not always available. Cassandra is something that often is considered to be an AP database, an available database, but it actually has settings that you can tweak that will tune it towards consistency. Of course, when you tune those settings, you're giving up availability in order to do that. So it's always a sacrifice. But what it really boils down to is very few, if any, systems are truly 100% consistent or 100% available. They typically make a choice to say that in certain circumstances we will be consistent, in other circumstances we will be available, and we'll just lean more towards one or the other. So most systems are trying to balance these two concerns, usually favoring one side or the other. Now, the interesting thing is, oftentimes when we build a system, we look to the database to provide a guarantee. So we will choose an available database, or we will choose a consistent database, and then we'll use that everywhere. But the reality is that's not always appropriate. And we'll talk about this more later, but basically what it boils down to is there might be areas of your system where you want availability and other areas where you want consistency. And if you rely strictly on your database, then that can be very hard to achieve.